Alright, conjecture questions. Conjecture questions are a special style of question. In theory, conjecture questions can appear anywhere in the course. They appear most easily now and then in the integration topic later on. In the exam, you're almost guaranteed to have one, if not two, conjecture questions. And you'll have one for this SAT. They all follow a pattern. And I thought we'd just work through an exam question together, but the pattern is do something, do it repeatedly, spot a pattern, prove the pattern. And the conjecture is spotting the pattern. So here we have a function. Consider the function f of x equals x cubed on x plus 1, where x is not equal to negative 1. On the axis below, sketch a graph of the function clearly showing axis intercepts as well as vertical asymptotes. So I think this is what you asked. If you're just given a random function, how do you sketch it? Alright, what you do is you grab your calculator. And for the rest of this year, you will have calculators available. Grab your calculator, set the view window between -4 and +4, because they've given you that, and between neg 15 and positive 20. So I'll do it on my calculator as well.
There's one thing I hate in the world. Having damn wet hands. Stand.
Yes. But you know, feel when you get like a certain amount
finish like one way was similar.
Come on, you guys should be ahead of me on this because I'm playing on the computer. What was the actual thing? X cubed on x plus 1. Alright. X to the power of 3 divided by bracket. Alright, before you even graph, you might as well check the view window. View window is between -4 and 4, and the y values between -15 and positive 20. They've given you shift view window. I think it's top middle. Yeah. And then set it to what they've given you. And then they've asked you to clearly sketch the axis intercepts and vertical asymptotes. If you're looking at this graph, what's the vertical asymptote? And you should be able to get it algebraically as well. What's the equation of the vertical asymptote? Yeah, good. X equals -1. It's that drop there. And if you are labeling all the points, how do you get the axis intercept? Just with a calculator. It's gsolve root, and I'm guessing it's going to be 0. So now what you need to do, and I'm not going to attempt to do it on the screen, but you can do it on your sheet, is draw that on the graph provided. I would put a dashed line vertically in there in pencil to show the asymptote, and label the point. If they've asked you to label a point, label that. If you want to give yourself some guidance on where it turns, you can see there's a minimum here. I would hit gsolve min, and that just helps you line it up nicely. Even though they didn't explicitly ask for it, gsolve min means you're aiming to turn your graph there. So give it your best shot of sketching, and note this is a past exam question. And so in the exam they can very certainly ask you to draw graphs. Actually, yeah. Gold, there's some good graphs. Calculator Excel.
Yeah, it doesn't have like an axis.
Oh. Shift setup. You want grid on. Yes, axes on. Better.
That's not even the right graph though.
Grid.
It is. You just need to check your view window correctly. So hit G shift view window. Oh yeah, that one. Send me these numbers and
Oh.
I'm going to give you.
Why would you do that?
What's the number?
Bang.
Not bad.
I like to do that.
Alright, so let's pretend you all have a beautiful graph and we can go on. The graph has two stationary points. One of these stationary points is at the origin. So as soon as you think stationary point, you should be thinking the first derivative is 0, meaning it's flat. Find the x-coordinate of the other stationary point. Now, if you're doing exam questions, and we are, note the mark scheme. Mark scheme meaning 1 mark. They are not expecting you to differentiate, create a sign diagram, and solve it algebraically. 1 mark is just G-solve minimum. Yeah? You know how we did that before? All they want is this number here, x equals minus 1.5. So your answer for that first one, all they want is the x-coordinates, x equals minus 1.5. And as a general rule, for all conjecture questions, I would try and avoid writing in decimals. You're more likely to spot a pattern if it's fractions. So how would you write that as a fraction? Yeah, lovely, minus 3 on 2. I would, and your calculator can do that conversion if you're unsure of it. But yeah, so I would say that is the best answer. They would accept either answers. So they would accept either for that 1 mark. Alright, now consider the function. G of x is x to the n, where n is a positive integer greater than 2 and x is never equal to minus 1. For all the possible values of n, g of x has two stationary points. One of these stationary points is at the origin, the other is at point A. Complete the following table in the form a on b, where a and b are integers. Now n, they've told you, is 2, gives you a minus 2 on 1. If you look at the graph on the previous page, what they've actually made you do is the 3 version of this. So they've walked you through the second step. And you guys can now put in that, because that's for n equals 3. And then can you grab your calculators and repeat the trick again for 4 and 5. So it's a calculator one. You put in the leading, or the top power of 4 and top power of 5, and repeat finding the stationary point. I will do it as well. Delete 4. G-solve max. And hopefully when you did to a power of 4, you got minus 1.33333 and happily shifted that in your head across to minus 4 on 3. And then go again, and you can probably guess before your calculator even verifies it for you that this is going to be minus 5 on 4. Yeah. No. If you're going through the exam, I would put little stars next to things that you'd be happy to check. But to be honest, you're going to check it by proving it in a minute anyway. So like, yeah, as soon as you reckon you've got the pattern, just fill the pattern in. Yeah. Alright,
What did you see?
guys, it is recorded. On the basis of your answers to part BI, make a conjecture about the x-coordinates for point A for function f of x. Alright, so basically we need to spot a pattern and then use the language they've given us above to describe the pattern. So the thing that's changing here is n. And you might have noticed here, n being 2, 3, 4, 5. It's only 1 mark, so I will be saying something along the lines of the x-coordinates, the x-coord for point A for g of x is, and you then need to convert n to this. So I would say that is minus n on n take 1. You see how if you've got, this is the n value, that's the n value and 1 less than the n value, 1 less than the n value, all the way through for the table. And it is this statement here, they're really hunting for the mark, but I would wrap it in a sentence just to be nice and clear. So you're looking for this as the x-coordinate of the turning point. Yeah, is that making some sort of sense? And you can probably predict where they're going next. They say, all right, great, you made a conjecture, prove or disprove your conjecture. They always say prove or disprove. I've never yet seen one that is actually a disprove. All right, so what we're going to do here is start off with the general case. Our general case for g of x is x to the n on x plus 1. And what we're going to do is we're going to hunt the stationary points. So because this was describing the x-coordinate of a stationary point, we're going to hunt the stationary points. And hunt the stationary points is first derivative, set it equal to 0, find where it turns. So we just do all of that, carrying this n with us, and at the end we should end up with an x equals this as one of our two solutions. The other solution being 0, because they told us the other one. So let's find the first derivative, g dash x. If we're hunting that, I would say u is x to the n, u dash is n x to the n take 1. V is x plus 1, v dash is 1. Therefore, g dash x is u dash v minus v dash u on v squared. And then we want to set that equal to 0. Now, note that if this is ever going to equal 0, we're really looking for the numerator, or the top part, to equal 0. The bottom will never give us a solution. It's only the top that we're interested in getting a solution. So therefore, I would just take the top and make it equal 0. X plus 1, bracket, bracket, n x to the n take 1 minus x to the n equals 0. Now, if you're hunting this, a couple of things you do. I'd be tempted to expand this out. Would I? Yeah, let's try it. Alright, let's expand this out.
That's all we're going now.
Sorry. Alright, if we're expanding this out, x multiplied by this, worth reminding ourselves that that's really an x to the power of 1. X to the power of 1 multiplied by x to the n take 1, we're adding the powers. So that gives us n x to the n, that's that, plus 1 lot of it, plus n x to the n take 1 minus x to the n equals 0. That's there, that's that expanded out. Now, we're pretty close to factorising. So the goal for any of these equal to 0 ones is you're trying to factorise it and set up a null factor law setup. So I'd be taking out a common factor here. And there's one common factor that we can remove pretty comfortably, and that's x to the n. And if we remove that, we're left with an n plus this with x to the n taken out. It is a bit disgusting, so I'd almost be thinking off to the side, if I have x to the n multiplied by x to the something equals x to the n take 1, what must the something be to get me back there? Yeah, neg 1. So do feel free to take it off to the side, because if you're factoring out x to the n, you're pulling it out here, and you know you need to multiply it by something to get there, so I'm thinking this is really n x take 1 minus 1 equals 0, because I've factored this out. Now we're going to get a solution from each of these. One solution from here and one solution from here. The solution from here is easy. If I want this whole thing to equal 0, one solution is just x equals 0. And we knew that. We knew there was a stationary point at 0, so that's a bit of a trivial solution. That's kind of confirming we're on the right track, but it's the one they told us about already. What we're more interested in about is n plus n to the x minus 1 equals 0. We want that to equal 0. Now there's only one lot of x, so we can basically solve for it directly. I would start throwing stuff on the other side. So I'm going to take one, or add 1 to both sides and take n. I'm then going to divide both sides by n. And then I'm sort of going to remind myself that this is really 1 on x. And now we've got to go through a bit of legwork to get x by itself. You can cross multiply and then drop this down the bottom. Are you happy just to flip both?
Yeah, can you just say it out?
You can. The reason it's allowed, if I have, say, 2 on 4 equals 4 on 8, they're both a half. It's equally true that 4 on 2 equals 8 on 4. So yeah, you're allowed to do a flipsies, and it does kind of make sense here, so we're going to flip it. X equals 1 take n on n. No. I said flip and then just didn't flip.
No, they all said R.
That's not right.
No, that's not right either. N take 1. 1 take n. No. Trivial. Alright, this isn't exactly the same as what we've got up there. Up there, we've pulled a minus 1 out the front. And they would want to see you go this extra step. Are you happy that if I take a minus out of the bottom, so I take a minus out of the bottom, I'll be left with x equals n over minus 1 plus n? Because I can take that negative out of the bottom, and then if we were tidying it, that could be minus n over n take 1. So we have ended it the way that we wanted to go. It would just require that last little shift. I think that's our first exam conjecture question. Actually. Alrighty. Next thing, I'll talk a little more and one more question, and then I'll let you guys get some work done, and in the second half I'll teach you the next bit. Rates. About this time last year, I went to an Ed Sheeran concert in Adelaide, and as I was sitting there bored waiting for it to start, I came up with this example. It is a model of people entering the Ed Sheeran concert. I know, it was such a romantic night out with my wife, yeah. We went to Ed Sheeran together, and I came up with this. The number of people at the concert was about 55,000, and this is kind of how it works. If gates open at 4 p.m, there's a bunch of like uber excited people waiting out the front at 4 p.m, ready to go in. But because it doesn't start until like 7, not many people are coming in, and then the organised people drift in, and then there's about this point the people who have a job and actually need to like transit there afterwards are entering in. And you're happy that somewhere here is the steepest part of the line, like people are coming in fast. And then those who have had maybe a bit too many pre's are rocking up, but there's not many people doing that. So there's slow arrivals here and slow here, but at some point the line is the steepest. This steepness is what we call a rate. It's the first derivative, and in our case here, if we are looking at the number of people according to time after 4 p.m, dp dt is the change in people over the change in time. This represents the rate at people entering. And if we're looking at people and time is in hours, dp dt would be people per hour. So at this point here, there will be a certain number of people per hour entering. So you can say that this is the rate of people entering. And yeah, you can write that down. dPdt, rate of people entering. Where is this rate maximized? Now if you've got a curve like this, here, if you visualize it, are you happy that the steepest point will actually be where it goes from concave up to concave down? You can probably see it better on mine, but there will be a point where that graph goes from concave up and starts heading concave down, and at that point the graph is the steepest because the slope keeps increasing, and then the slope starts decreasing. At this point here is where the second derivative is equal to 0. So we're looking at, I know we're not using this, but f double dash x equals 0 gives us that point there. So where the second derivative is equal to 0, or dp squared over d squared t, like where they put the 2's in the top, that is where the rate will be maximized. Now of course there's lots of real life applications to this. It means that you don't need many gates open or many security staff here or here. They're still rocking up here and here they've moved into the main stadium. It means that you need maximum gates open at this period here. And they'd be looking at this for AFL, cricket matches, concerts, etc. Like, I'm sure whoever manages Taylor Swift's company will have some sort of software that will predict the number of people arriving. Using a model like this and using rates, they can work out what their staffing needs are. Like, these things, lots of people tend to be kind of predictable. The model, of course, breaks down, because this is not a very fancy model. If dP/dt is always positive, what does this imply? Like a positive number here, what's that implying? I mean, for Taylor Swift it might be true. Positive number here means people are always going into the stadium. A negative slope would mean people leaving the stadium. If this model was, fancier, it would carry on a bit, and then at some point it would drop off, a couple of people leaving early, then very steeply as the official ending goes, and then those Uber fans that take ages to leave at the end. So this function would basically mirror over here. That would mean the slope being negative would mean people leaving. But my model never goes negative, so it's not the most realistic model, because everyone would still be in the stadium according to this model. What is the rate of entry at 5 p.m., 6 p.m.? If we were going to do this using a calculator, we can literally, do you guys want to do that using a calculator? Oh, well, you'll get to questions, but yeah, okay, let's do it using the calculator. There's two ways. Do you guys want to do it in run mode? I haven't shown you run mode, so let's do it in run mode. So can you just go to regular, ordinary mode here? And we want to find, what was it, the rate of people entering at 5 p.m. The rate of people entering at 5 p.m. is when x is equal to 1. Can you guys go options on your calculator? Press calculus, and then go ddx. And then you're going to put in the equation. So 55,000 over bracket 1 plus e to the power of minus 2x. Your calculator doesn't like t, but go x, plus 5. And you are interested in the derivative of this function 1 hour into the event. What this implies is that 1 hour in, meaning at 5 p.m. after gates entry, nearly 5,000 people an hour are going in. 4,969. And you can see that 1 hour in is not very steep. If you want, can you change that to 6 p.m. and look at 2 hours in, and it should increase.
You know what, that's true.
Yeah.
So 2 hours in, the instantaneous rate is 21,000 people, or a bit over, per hour at that instant. Alright, one more example that the book made up, and then we'll go do some practice. Alright, so rates tell us the speed at which something's happening. So h-t could be the instantaneous rate of ascent on a Ferris wheel, c-t could be a person's instantaneous change in lung capacity. And units do matter here. Those of you doing physics will be well aware that sort of people get iffy about units. Meters per second, the per implies a rate. So let's look at their example. According to a psychologist, the ability of a child to understand spatial concepts is given by A equals a third root t, where t is the age in years between 5 and 18. Find the rate of improvement or ability to understand spatial concepts when the child is 9 years old. I won't go through and do it, but when it says rate, what it wants is the derivative of this and then sub n 9. So if you find the derivative of this, it would be what, 1/9 t to the minus a half sub n 9. It'll work out fine. Same with 16 because I've chosen a nice perfect square. Again, it'll work out fine. And here, it's a bit hard because they haven't given you good units to work with. It's just the rate of it. Show that dA dt is greater than 0 and comment on the significance of this. This means the slope is always positive. What that means is that, in this scenario here, a child is always increasing their ability to understand spatial concepts. So from 5 to 18, it will increase. The second derivative is always negative. So if you found the second derivative again, you could show it's always negative. Does anyone want to have a crack at the significance of that? And then you can have a crack at my age.
You're always getting smarter at a less rate.
Yes.
Yeah, I don't know how to explain it, but yeah.
Yeah. The graph looks like this, meaning the slope is always positive, but it's happening at a decreasing rate. So someone learning at age 6 will learn far faster. That slope there, the rate of their learning, will be lower than the rate here. And that is true for most areas of knowledge. I'd say there's a blip in year 12 where you guys just like blip it, and then next year if you take a gap year it just reverses. Anyway, but according to this psychologist, yeah, you're looking at that. So it's part of these questions are calculus, part of them are interpreting a model given. And I'll give you a little while to do some practice on 3F, and then we'll have a look at 3G in the second half. Sound good? Let me just pause it.